Hi, welcome to the ARC Future Timber Hub Research Showcase. Today's presentation is of the University of Queensland Structures and Architecture Showcase, and this is series 1 of the 5 presentations. Before we begin, I'd just like to do an acknowledgement of country. The ARC Future Timber Hub, administered by the University of Queensland, acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australian and global society. So I am the host of today. My name is Kelly Reichmiller. I'm the ARC Future Timber Hub Manager. And I've also got Dr. Lisa Ottenhouse, who's our chair for today. She's a lecturer at the University of Queensland School of Civil Engineering, and she specialises in timber structures. So just a little bit about the ARC Future Timber Hub. The ARC stands for Australian Research Council. We're an industrial transformation research hub to transform future tall timber buildings. The aim of the hub is to transform the Australian timber construction industry by generating the skills, knowledge and resources that will overcome current technological and social barriers that limit the application of timber to tall structures. We've brought together experts from industry, government, academia. So we've got the Queensland Government, Department of Agriculture and Fisheries as a partner, University of Queensland, the Queensland Fire and Emergency Services, Hine Timber, Arup, Lendlease, Scion, the University of Canterbury, Griffith University, and the University of British Columbia. Plus, with individual projects within the hub, we have extra partners on top of that. So we've formed a unique partnership that spans the entire timber supply chain, from primary producer to construction regulator. Our interdisciplinary team includes product manufacturers and wood scientists, architects and structural engineers, fire safety engineers and construction managers. So I'll hand you over to Lisa to introduce.
Welcome, and I will be chairing, so I'll also be doing the Q&A. And today we will hear about 2 research projects that are administered here and carried out here at the University of Queensland. So the first project is on prefabrication and digital fabrication strategies for large-scale timber construction, and the project seeks to combine hub partners' expertise in digital fabrication, prefabrication and manufacturing automation to develop new beneficial structural components and systems suited for large-scale or modularized timber structures. And that project will be presented together with another project on the alternative uses for undervalued sawmill products in innovative timber structures, which investigates the design of innovative and alternative structural timber systems and technologies that adapt low-value timber products such as sawmill offcuts. And I'll just introduce today's speakers. So Harry Mills is a designer and PhD candidate with the Future Timber Hub at the School of Civil Engineering here at UQ. And Harry's passion is for environmental and climatic responsible design. He was the 2019 Gottstein Fellow, and the scope of his research is developing tools and strategies to support built environment uptake of underutilized and marginalized timber resources. Then today, we were also going to have Dr. Joe Gattas, and Joe is a senior lecturer at the School of Civil Engineering here in the Faculty of Civil Engineering, Architecture and Information Technology, but Joe has just recently become a dad, so he sends his apologies since he cannot join us today, but you're most welcome to send any special inquiries to him via email. And so Harry will start presenting and then he'll hand over to Kim. And Kim is a fellow in civil engineering and architecture at the School of Architecture in our Faculty of Engineering, Architecture and Information Technology. And Kim is also a registered architect with his own architectural practice. So I'll now hand over to Harry.
Thanks, Lisa. Hello, everyone. I'll just share my screen. Just confirm with Lisa and Kelly, you can see that okay? All right, no worries. So yeah, hello everyone. I'll begin by acknowledging the traditional owners of the land on which the presentations today occur. I also pay my respects to elders past and present. Today I'll first present underutilized timber and resource responsive design strategies. This work forms part of a larger PhD project that I'm completing under the guidance of Dr. Joe Gattas and Kim Baber, which is looking at opportunities for underutilized timber in the built environment. Following, I'll present some of Joe Gattas' work looking at prefabrication and digital fabrication strategies for large-scale timber construction. I'll begin by giving you an overview of the softwood timber product industry here in Queensland. This image is of the resource. This image on the screen here is a resource referred to these days as southern pine. And it's a plantation up in the Tullara forest situated between Gympie and Maryborough here in Queensland. The plantations in Tullara forest and the surrounding Fraser Coast region are mainly hybrid trees, genetically modified over several generations from blends of species like carabine and slash pine. In Queensland alone, there is near 150,000 hectares of southern pine. These trees grow to an average age of roughly 28 to 30 years of age. Typically speaking, there is approximately 1,000 stems or trees per hectare, which after thinning, which is the deliberate act of felling the tree for the benefit of higher quality growth and to meet intermediate demand, around 400 stems or trees per hectare will be there when they're finally felled. The thinning occurs roughly between the age of 16 to 22. These trees are felled and processed on site and transported to a milling facility. Often to meet demand, logs can be transported many hundreds of kilometres across the country to meet the demands of different sawmills in different states or territories. In Queensland and for the southern pine resource, the trees will end up at Hine & Sons in Maryborough or AKD in Caboolture, they're the two biggest ones. It is at this milling stage on this third row here of the pictures that the research is and this presentation, the ones going forward, are really focused on. So the following with that background of southern pine, I'm going to introduce you to a couple of terms of utilised and underutilised timber. In the current market, you have two product streams for the sawn, board and planks. The utilised timber, which is the structurally and visually accepted wood. The underutilized timber is milled, soft, sawn, board and plank, which fails structural grading due to structural and visual characteristics. This is often referred to and has been referred to as utility grade, out of grade, or non-structural. This is the basic supply chain. After it's felled and barked, there's a scanning and scraping of the log, which will generate wood chips, residues, the sawing and product extraction, and the structural board and plank can go to a residential market, low-rise market, or can go towards engineered wood products and the glue lam CLT. The underutilized timber, though, can go towards engineered wood products. However, typically it does not occur to a great extent at the moment. Packaging, which is a big market, and some form of board and plank. However, due to the demand for wood chip and export overseas, more and more is getting chipped. This is another diagram of the different markets and streams for which the underutilized timber or utilized timber can go. The red is the utilized and the blue is the underutilized. These are areas of wood which I would classify which is marginalized, or there's opportunity for value adding, and it occurs right across the supply chain. For the purpose of this presentation, we're focusing on the board and plank products. This is on the screen here is a typical sawing pattern displaying the board and plank product extracts. It has been visualized as the red as utilized, and underutilized is blue. In the center, you can see the juvenile or the younger growth wood, while on the periphery you've got the outer rim, which boards maybe consist of sort of wane and other sort of growth and processing defects. Both structural and visual characteristics like knots, wane, distortion, coloration, low and fluctuating density properties are just a few that can be found in UUT or underutilized timber. When these are found together, the timber is classed low in grade and has low consumer acceptance, which therefore means it's low in value. Presently, we can define underutilized timber by its failing grade, low quality in terms of structural and visual characteristics, low in financial value, however, high in volume. Issues such as designer awareness, consumer acceptance, legislation and code compliance are challenges that must be addressed for UUT products or UUT resource to gain market uptake. So who's responsible for the deal with this volume of wood? Underutilized wood is not a new concept. Indeed, low grade and low quality wood has been around since the earliest of days of timber felling. In the present market, it can be argued that the forestry, milling and manufacturing area is aware. However, outside of this area, in the designer or builder or to the end users, there's very little awareness of this volume of resource. This research is coming from a designer background, aiming to initiate awareness, interest, and ultimately some responsibility with design practitioners. I'll present now a preliminary responsive tool, which looks to address some of these aforementioned problems. This is a Rhino grasshopper tool that consists of two components. This is a tool for post and beam building typologies, which has a structural analyzer for slab, beam and column design for CLT and glue lamp structures, and a resource consumption visualizer, which provides big picture understanding to how much wood is being consumed. The tool takes into account the nature of post and beam buildings, which have vertical load carrying mechanisms. The structural analysis figures out the required loads of any conceptual model through analyzing projected building loads like vertical, self-weight, distributed foreloads, and lateral loads. Wind forces are typically factored in through the shear core and external bracing. The purpose of the visualizer is to enable practitioners a comprehensive understanding of how much material they're actually specifying. So this is ideally would be utilized in the conceptual phase of a project. And the main feature of this is to understand how we can use our resources more responsibly. I'll bring you back to the previous slides on underutilized timber and to really pinpoint the problem here. For every log that gets sawn for board and plank product, up to 40% of it can be classified as underutilized timber. There's very little market for it. However, critically, there is a significant volume. With little expansion of softwood plantations for some time, coupled with current demand for timber increasing for its sustainability credentials, the mass timber push, and a local market which is becoming more reliant on international supply for timber products, there is serious opportunities to value add for underutilized timber for built environment purposes. I'll jump in and give you a fly through of the tool. So the design toolboxes are treated discrete. The slab design is based on a local manufacturer's guidebook as to current standards and quality sizes for typical slab and given for the proposed loads, serviceability, structural dynamics, and strength under vertical loads, and simplified natural frequency checks. Beam design is similar to slab, size for strength limit case, dead and live loads, and serviceability deflection limits. As with the beam, column design is sized for strength limit in case of dead and live loads, although omitting serviceability deflection limits given the actual deflection over multiple stories being minor. Some of the assumptions on neglecting transverse loads, non-critical, not significant to the total volume of building. we can play around with the sizes, the different span, beam length, so forth. To verify this tool, we're really quite fortunate in that in Australia we have two recent building examples in International House and King Street that we could use to verify the accuracy of this, which was really quite successful. Now, this tool gives you an overview of how much volume of wood and the sizes are being used. So if we look at International House with the material which was used, with no underutilized timber at all being used in the project. However, if we're able to implement and add underutilized timber to some engineered wood products through CLT or glulam, and if we're able to drop this to like a 40% uptake, we can drop 7 hectares of forest immediately. And so just by implementing a little bit of underutilized timber or looking to specify this further, we can really understand how much volume of wood we can reduce. This we can visualize further with the forest and the trees. Now, this would be quite a handy tool when you're trying to convince clients to specify a certain product, the benefits for that. And the underutilized timber in terms of how much we can actually use, even just if we could get it to 20% uptake, we can really drop the amount of land use and how many trees we're ultimately using. So underutilized timber has the potential to be incorporated into different products, and through providing designers with sustainable tools like this, really gives options for them to specify alternative and more responsible timber products. This is where we're coming from as a design, trying to implement new products and systems, and ultimately trying to generate new products and build prototypes. Some of the other research that I've been involved in through the PhD has conducted interviews extensively across the building supply chain, and one of the key takeaways from that was that we need built prototypes to see what this resource would look like. Kim's going to give you a good overview of some of those products and systems, and I'm going to run through some of the tools and ideas that Joe's been generating for the project now. So utility grade processing toolbox has been developed to import and utilize quite a vast amount of data we get from the manufacturer. So board data designed for product and system design. Manufacturing board processing data is extremely rich, including board images, stiffness and grading, and defect type and location data. It is about 3.5 megabytes per board with two boards produced per second. We are the only building design research group in the world with direct access to commercial board and production data, which has allowed us to pursue some really interesting investigations, as you can see on screen here. But to enable that, Joe's been able to build a toolbox to import the XML manufactured data into MATLAB resource database, which can store inventory information for any boards they're happy to use. We can inspect boards in full color to look for certain visual features. The main features of interest are defects. So some of the characteristics which I was highlighting before of underutilized timber and they're really already located in the data packet that we receive from the manufacturer. So you're able to access the data directly, for example, to find clear wood regions or best face or best length, which contains the fewest defects of the particular type. Or primary interest our primary interest though is the stiffness data, which is stored as an overall board average modulus of elasticity, or MOE, but also as continuous MOE value sampled along most of the board length in Heinz mechanical grading process. This data is what Joe's been accessing for the structural product and system investigations, and this will be further elaborated on with Kim with some of the examples he's going to show. Another example Joe has been leading is nail lamination, and he's done that with recent graduates from the civil engineering cohort here. This is a plot of board average MOE values on the y-axis and minimum MOE values on the x-axis for typical underutilized boards. In laminating boards, we can mitigate the weaknesses across the section. So for example, on the right, pairing high and low average stiffness boards. What we've found is that for board laminations or quad lamination is sufficient to completely homogenize a set of underutilized timber boards, effectively raising the average MOE to 8,000 MPa for the entire feedstock, as well as substantially eliminating and localized weak regions of the board. One of the last things I'll present for Joe is it's a work in progress. It's an extension and a bit more beefed up version of the tool that I presented earlier. This is Joe's looking to integrate some of the tools and concept of that earlier one for real-time connection design tools, essentially developing a Python library of parametric models for element and connection sizing, as well as design heuristic tools for direct section lookup. They are open source and are intended to both help with initial concept sizing, as well as provide some building blocks towards complete algorithmic part generation, for digital fabrication. This is a bit of a work in progress, as I mentioned, but as a brief, simple illustration of what we're driving towards here is a glulam member with two tensile load cases, element cross section and connection sizing, generated in real time based on governing load and preferred connection bolt size. Colored, they're colored in the outlines, colored outlines are the load case sizes, black outline is the overall size from the available section sizes. Here is a mock-up of the end goal, but these tools are fast enough that we can create structures in which every element and connection are self-sizing in real time. This truss has 7 elements and corresponding connections. And as we apply load factor to the scale element loads, or as we change the bolt size preference, you can see the truss attempting to size itself or remove elements when there are no sizes available for the given load. So on that note, I think that's a good overview for some of the digital strategies that Joe's been working on, and a good understanding of the underutilized timber or out of grade non-structural wood, which we have available to us here. So I'm going to hand over to Kim, who is in the collab, the architectural collab, and he's going to run you through some of the work he's been up to.
Thanks very much, Harry. Hi, everyone. So my name's Kim Baber. I'm a fellow in civil engineering and architecture. I'm actually an architect. I have my own practice, and I've been teaching in architecture part-time for many years now. But my work that I do in the Timber Hub is closely related to some of the student work that we've done for the last decade here at UQ. This space is what we call the collaborative laboratory, or the collab for short. And it really is a space that our students in the School of Architecture, but also between the School of Architecture and the School of Civil Engineering, can collaborate on projects. So The types of things that they might make in here would be little models, as you see in every architecture school, but then they also get to build full-scale prototypes. So this is a recent project that some students in the master's course were looking at building a screen for a tower with a little operable window. So they learn how to actually fabricate these at 1:1 and develop their design accordingly. So we really see a strength to our teaching here, being able to offer students the opportunity to get involved in hands-on making, and that leads them into potential research higher degrees. What I'm going to talk about today, you'll see this kind of weird shaped truss behind me here. This is one of the first, what we call an inventory constrained design projects that we worked on about 2 years ago. It's quite a funny shaped truss, but it's deliberately so. And I'll explain that when we get to it. One of the key things that we're looking at when we look at underutilized timber is what you might be able to do with the timber if you were to take out those defects. So if we were to start off with a piece of utility grade stud and we cut the defects out, of course you end up with all of these odd shaped pieces, and that's really not of much value to people. However, with our computational design processes and our analysis tools that we're using in MATLAB, we are able to automate the design of custom shaped structural members and structural elements such as this truss, which look to find a home for each piece of short length of timber that results from a piece of utility grade once you cut the defects out. So one of the things that we look at is, like, what you do with small pieces of timber. You can make specific shapes. You can look at how we might be able to join these pieces together without the need for a mechanical fixing potentially. We can do that through our computational design and our digital fabrication. So we are really interested, in a way, to summarize it, we're interested in what we can do with undervalued timber that comes from either a shortening of a member into small pieces that are dimensionally undervalued. We're also interested in manufacturing byproducts such as peeler core. I'll talk about this in my presentation as well, but we have quite an extensive range of projects where we look at ways in which we can use short length peeler core and join it in novel ways. We are also interested in offcuts from, say, a CLT manufacturing process. So here we have a column which is laminated circumferentially, and it's made out of what we, for example, we would envisage being an offcut from a billet in a CLT manufacturing process. We're able to use the technology from both the computational design tools and also our digital fabrication to look at how we can yield greater value out of using what would otherwise be seen as pieces of material, pieces of resource that otherwise have very little value. So I'm going to jump onto my screen and I'm going to share my screen and present the background behind all this research. So let me just swap modes here. Okay, you can see that. So as Harry introduced, one of the core parts of this project is to look at how we can both generate an inventory of undervalued timber and then what we can do with that inventory. So if we just re-summarize Harry's slide on what happens to the timber from the stem, obviously after milling we have both usable boards which would be clear and reach the required MOE over its length. But those that have defects on the bottom there are often used for other applications, and in some cases that turns into chip. However, what we're interested is what we're interested in is what we might be able to do if we were to work with these short lengths. And so once you do cut those defects out, we have, in effect, an inventory of unique lengths of structural grade timber. So we do have all of this data at hand, as Harry described, and we're able to analyze that in a very fast and sophisticated manner that will generate this digital inventory of short lengths. On the right-hand side, you can see here what we might yield from a typical pack of utility grade timber in terms of the usable lengths that would actually achieve the required structural MOE once you cut out the defective lengths from the stud. So as you can see in this example right behind me here, one of the first projects that we looked at, we're looking for structural applications where you are already working with short lengths of material. So trusses are a good example, and curved trusses even more so, where by definition, every element within that structure is already being cut to a shorter size than it's likely arriving in the workshop as. So here's an example of a curved truss where we looked at our inventory. We use what we call a parts assignment heuristic tool, which takes all of the parts available in the inventory and it assigns them to a location in the structure based on a set of rules that we can make up, a heuristic that allows us to program in desirable deviations from the target geometry or certain lengths. Here you can see it running on the left-hand side. It's rapidly sorting through all of the combinations that might be available. And so this was a project that we ran 2 years ago where we looked at developing a uniquely shaped truss, but again, each element within that truss is machined digitally through our CNC router, and we're able to convert the process of inventory constrained design into digital fabrication. Another example which took that process and really applied it at a more sophisticated computational level was a project that we entered into the IASS, the International Association of Shell and Spatial Structures, as part of a competition where we worked with Professor Jane Burry and Chun-Wei Chen from the Swinburne University of Technology. And this project was looking at curved arches. So again, a structural type that inherently requires small lengths in order to be constructed. So we were combining two form finding methods. We were actually looking at a funicular structure, and some of you may be aware of the funicular geometry that Antoni Gaudí worked with in masonry over 100 years ago. This project was looking at how we might look at a combined optimization tool where we used both a funicular modeling tool combined with an inventory constrained computational model. Here's the types of models that Gaudí worked with over 100 years ago. And in these models, he actually physically suspended lengths of string and chain in order to derive the optimal structural geometry for, in this case, a masonry arch. So as I said before, when we build the parts assignment heuristic, we feed in constraints, which in effect constrain which parts of the inventory we're able to utilize in the structure. So in this case here, we have a given form, a given curvature, and we are able to apply, for example, the amount of curvature that a certain given length of timber may yield once we define the amount of material taken out of it. So here you can see a little video showing when we change the curvature in a given arch. On the right-hand side, you can see our inventory of unique lengths, and it goes through and sorts out in real time which parts would be assigned to that arch and in which order. And so that's quite a sophisticated, what we call a parts assignment tool. And we've run this in combination with a digital funicular form finding tool. And so this is using Grasshopper in combination with a plugin called Kangaroo that allows us to hang chains in a virtual environment. It also allows us to, in effect, tweak the lengths of those chains or strings, like you can see on the right, in a way that's actually a virtual version of Gaudí's hanging chain model. So we're able to have both a form finding model that has its own optimization set of rules, which is about funicular geometry. And we combine that with the inventory constraint from our inventory of short lengths. So here you can see after we've generated that initial hanging chain, we can then run our parts assignment heuristic to map onto that geometry where each part of our inventory can best fit. However, we can give it a certain amount of tolerance, and we can say, okay, let's try to get every part within 5% or 7% of its target geometry. And it tells us how close we can get after sifting through thousands of variants. But the kind of neat thing with this project was that once we'd arrived at that, let's call it a best fit, it's not necessarily the perfect fit, but it would be the best fit with that given inventory. We can then go back to our funicular form finding process, and we actually relax that model in order to meet the target that has been given to us by our inventory. So in effect, it's telling us how much to shorten those little pieces of string in the model and therefore meet the constraints of the inventory. But at the same time, during that relaxation, the re-relaxation of that model, it's also deriving a new, slightly different funicular geometry. So we're able to optimize both in funicular geometry as well as the parts assignment of the unique inventory of short lengths of timber. Now, our challenge was also to use utility grade for the structure in its entirety. Now, this structure was kind of very interesting in the sense that it did involve these three-way joints, these branch joints. And by definition, each one of these joints were unique in the way in which each member intersected each other in a three-way geometry. So one of our challenges was actually to look at how we might be able to construct this complicated three-way node out of simply two pieces of, in this case, 90 by 45 utility grade stud. And so you can see here that it's actually made out of just two blocks, which are paired top to bottom. And we create this filleting between the pieces that allows us to transition from one geometry to the next. So again, you can see that this computational processing of the transition of each joint could be done through a parametric model. And obviously, each one of these is unique, as you can see. It finds the intersection paths of each of those pieces of timber and generates those the geometry of each one of those blocks uniquely. A simple lapped dovetail joint was what we used to join each one of the members inside the arch itself. And again, if you think about structures that are necessarily using lots of small pieces, what we want to avoid is lots of mechanical fixings, lots of fixings that involve screwing or bolting, for instance. The other constraint, which was part of the competition brief, was that this pavilion that we designed needed to be packed up into suitcases and disassembled. So it had to be completely deployable in its context. So the structure that we entered in this competition was for a 4 by 4 meter pavilion, and we stretched a fabric over the outside of that timber frame as part of the exhibition that was part of the conference in 2019. So each one of these panels was parametrically defined and sewn and stitched over the top of outside arches, and there's a little seam that you can see that gets entered into a groove in the timber. So we made this in the workshop here, and you can see, for instance, our CNC router machining each one of the components in the arch. And we did some hand finishing, but largely this was done by CNC routing. And here's a pair of these nodes, 2 pairs in fact, and you can see how they were machined. The machining was only from the top down because we had a 3-axis CNC router. That's all we had available for the project. But the idea of these is that they are machined from one side only, then flipped and connected back to back. And here you can see the way in which these nodes connect. So we did test that node, and apparently we could get 30 kilonewtons out of it, which was reasonably good for utility grade timber, although the sections that we did choose out of that timber member were obviously defect free. That's what the fabric looks like. And we cut this out just simply on the floor with a grid and sewed it to stretch over the timber. Here you can see it being erected in the AEB structures lab. And as I said, the whole structure was designed to be deployable. Now, what's interesting, I guess, about this process is that really this pavilion is the demonstration of a process. It's the demonstration of an analysis process that we have developed in analyzing the inventory, but it's also a demonstration of how that process can be then turned into a 3-dimensional structure. And using a mass customization digital fabrication technique, we can use the processing power of the computational design tool in combination with a digital manufacturing. So this pavilion has toured a couple of places. It was at the University of Melbourne as part of Australia Design Week in 2020, just before COVID hit. And it was awarded a Good Design Gold Medal in the end of last year. So we're quite proud that it's being able to demonstrate some of the research that the hub is doing. Now, I'm going to move on to a slightly larger prototype. And in this case, it's looking at how those types of computational design processes could be changed in scale. So here is a node that we are looking at building up out of a series of small pieces, again, small blocks yielded from utility grade timber. In this case, a combination of 90 by 45, 70 by 45, 100 by 25 inch board. And it was really, I guess, part of it was inspired by the types of sophistication that came out of making that node for the previous project. If you were to imagine that we build a space frame structure out of peeler core, where the nodes, where the peeler core connect, could in fact be mass customized, what we were looking at is a way in which we could laminate in a block gluing method specific layups of lamellas that allowed us to overlap in both directions, unique combinations of small blocks. Here you can see that the node that accepts 3 peeler cores is made up of 5 lamellas in a combination of 90 by 45 and 100 by 25. And there's a study on the top left of the cross section through those, where we're looking to achieve as much overlap in the gluing of those lamellas. And on the right hand side, you can see the varying makeups of how they're glued side by side. On the bottom of that image on the left, you can see ideas for the tenon joint that we're looking to design into this peeler core. And here's the cutting pattern. So again, this is a process that we could automate through our inventory parts assignment model. where if we know exactly where those short lengths exist, we can cut them from those pieces of utility grade directly. And here's an exploded axonometric of how all of these parts go together. You can see the top stacking of the lamellas, and you can see the tenons that we are inserting into the end of the peeler cores. And here you can see it being fabricated. So what we're interested in is how the sophistication of the modeling of this node interacts with the sophistication of the parts assignment from our inventory. And it allows us to build bespoke structures, in this case with a node that has a huge amount of, I guess, smart geometry built into it. But what we're looking at doing is just actually having a fairly simple mortise and tenon joint that allows us to insert those peeler cores in a direction that's perpendicular to the tenon rather than parallel to it, so that we could imagine structures like this. Here are some examples that I'm showing. We have done some collaborative work with the Digital Timber Construction Lab at the Technical University of Kaiserslautern in Germany with Junior Professor Christopher Rabella, and we were due to have him come out with a group of students last year, but that got cancelled due to COVID. But these are the types of structures that we were looking at constructing a full-scale prototype from out at our Pinjarra Hills facility. So you can see here that the scope of how this type of node could apply itself to a whole range of different structural types has an almost kind of limitless potential. Now, the last one that I want to finish on is this circumferential lamination. So again, looking at how we can use dimensionally undervalued sections that might either be thin, say inch board, or might be offcuts, say offcuts of CLT. And we're looking at laminating those into a circular column. This is not something that's new. It's how they used to make timber masts for a very long time. But I guess the proposition here is that we're looking at making hollow columns for yielding the benefit of putting that material in the outer wall of the structure. So some test prototypes that we constructed were just simply looking at how we might use thin boards cut to a wedge. And in these cases, we were looking at a circumferential tendon that can wrap through those in the form of a hoop, both as a form of confinement reinforcing, but also as a fabrication strategy for how we can actually manufacture these elements. So some of the small scale prototypes that we looked at were literally, kind of a 1:2 scale model where we were cutting thin boards to a wedge profile, which would involve, say, a single rip through a member and then opposing its direction. But more recently, we've looked at what this would mean if you were to use offcuts of CLT. And so our latest project that we just started doing some testing on not even 2 weeks ago was the lamination of CLT wedges, which we imagine could be offcuts, but we could also, and what the way that we made it, just simply saw through a billet lengthways with an angle on the saw, and then you just simply flip those pieces back to back. So here's an example that we used with 115 CLT. This diagram shows a range of different possibilities for inserting a concealed tendon within between the outer lamella and the middle lamella as a form of confinement. Here you can see when we did the kind of rough saw of each of those wedges, which we then cleaned up on our CNC router. And this was the first dry fit. So you can see we can get them really quite precise. What we did is we used a series of cores or nodes, should I call them, like stiffening plates that were made up in this case of 3 layers of 17mm ply, but that could also be a CLT plate. This column, for the purposes of testing, was 1.9 meters high, 580mm diameter, with 6 of those nodes at 400mm spacings. And the way that we assembled it after we'd located those stiffening plates was to, in this case, we just simply glued it. We haven't used any tendon. And then we simply strapped around the outside to pull pull those glue joints together. There you can see the finished column. And we did test this just almost 2 weeks ago, and we managed to achieve a capacity of 3.2 meganewtons for that column, which was, the sample was 1.9 high, and it's about 580mm diameter. So I'm told that should be able to support a 6 to 8 story commercial building on a regular commercial office grid. So that one is relying on glue only, but as I say, we are looking at other methods for hoop confinement in the way of a concealed steel tendon. So key outcomes and future opportunities for this research. We've really been developing analysis tools as well as modeling tools, and the analysis tools translate the sawmill scan data into a format that is readable in our design modeling software. So that's a key development of our research. And obviously we're using that in design modeling tools. And we're really looking at rationalizing material usage through these novel structural geometries. And I guess that's where, as an architect, what I bring to the project is thinking about different possibilities for those novel geometries and how they might offer different spatial opportunities. And really, I guess, kind of challenging the norms of what we might typically use in construction applications. We're also developing processes for increasing the yield of structural timber from underutilized resources, and also how we might generate structural products from offcuts from manufacturing byproducts. So future opportunities, really, these are, as I said, a set of processes that we've developed. And the examples that I've shown you are either prototypes at 1:1 or kind of small scale pavilions that demonstrate how these processes can change our understanding and appreciation of the resource that's available and how we can translate that into novel structures. But they certainly are scalable, and that's what we're interested in. So how these design processes can be scaled into a range of different forest resources and other types of manufacturing byproducts. And I guess the key thing is that these tools are quite versatile, and they can be used with a range of different inventories and building applications. So thanks very much on behalf of myself, Dr. Gattas and Harry Mills.
So tomorrow we've got the second of our webinar series. We'll be focusing on the Department of Agriculture and Fisheries showcase. So we'll be looking at 2 projects as part of the department there, as well as one extra one from UQ will be showcased. So thank you everyone for joining today, and that's it.
Thank you.
All right, thank you.
Okay.